And so we begin the beauties of Gauss's law. I will point out at the end of this lecture, Gauss's law is equivalent to Coulomb's law, but it offers so much more elegance and insight in those situations where you can apply it. You need to have geometrically very symmetrical situations before you can apply or really work with Gauss's law, but it's when you can, you will celebrate how beautiful it was. Gauss's law was actually developed by Gauss for dealing with gravity, but we are going to apply it to electrical fields, and it is the first of Maxwell's four equations that we are going to be learning this semester. We begin with the need for what is known as a Gaussian surface. Here is a Gaussian surface. It's a balloon, but anything which has is a closed surface so that there is definitely an inside and an outside and an on the surface is a Gaussian surface. This would not be a very useful Gaussian surface because of its lack of symmetry, but it would be genuinely a Gaussian surface. That you are going to have to choose Gaussian surfaces for the problems that you do, and you will want to make them their symmetry match the symmetry of the electric field that you're trying to learn about. But I would, before we move on, I'll point out that Klein bottles would not be Gaussian surfaces because they don't have an inside and an outside. And maybe that's too much of a tease. But that's what Gauss's law is ultimate. So a piece of paper would not be a Gaussian surface. It doesn't have an inside and an outside. And if you were to open the bottom of this balloon, suppose it were to stay nice and round, but you made a hole in the bottom so you could get from outside to inside without passing through the surface, that would not be a Gaussian surface. Ultimately, where we're going is that we can know, if we know what the field is like at the surface of a Gaussian surface, then we can know what charge is enclosed in the surface. And vice versa. If we know what charge is enclosed, we can know about the field at the surface, which is perhaps a little bit vague at this point. First, before we get seriously into Gaussian surface, we need to talk about flux. The symbol will be a phi. It is an archaic word for flow, although we still use it today when we say the situation is in flux, or when that is, it's fluid, or we talk about the flux, which in people who do electrical work will in the course of soldering they will use a flux, which is something that flows over the joint and keeps oxygen away while you're making the solder connection. There are also flux capacitors, and that's just nonsense. This is a patch of area, and let us assume that there is water flowing through that area that I would like to talk about, the amount of flow. Well, clearly, water flowing this way, there is going to be flux through the area. But if the water is flowing parallel to that plane, then there would be no water passing through the area. There would be no flux. So clearly we have something where this flux property has to do with the direction of the flow, the direction relative to the area, and the area must also have direction. We define the direction of the area to be normal to the area. And right now we have a little problem. Is that normal pointing up or normal pointing down? But don't worry about it. Here's one more. The flux through this area is going to be the dot product of this vector representing the area and the water velocity vector. That only the parallel component of this one would contribute to the flow, and in this case only the parallel component, which is 0, and hence there is no flow. So there is this notion of flux as this dot product of the area vector and the flow vector. Okay, so there's the idea that we've established. That in the case of electrical flux, we are not going to have something physically actually flowing through the area, but instead what these black vectors would represent would be electric field. The blue vector again is the area, and again it is the dot product of those two. And when we talk about a surface, a Gaussian surface, let's pull a Gaussian surface in here, that we want this whole Gaussian surface, which they are physically by shading trying to show you that it is a surface that encloses a volume, and there's an outside and an inside and on the surface, that they have cut this up into little patches of area, and you can see that perhaps the geometry, the artist's attempt is not real good, but these blue vectors are all the area vectors. They go normal to the surface and they go out. That was a confusion we had here. Does this arrow go up or down? But now there is no confusion. That the direction of an area vector is normal to the surface and out of the surface. And so if we look at this little patch here, we have the field, which is all of these purple lines here. The field dotted with the area is going to get you a flux that is less than 0. That's the angle between those two is bigger than 90, and so when you take the cosine of that, after all this is a dot product, you get a negative value. That to flow into the surface is negative flux. Over here on this side, that little patch has an angle between the area and the field that is less than 90, and so you get, when you take the cosine of that, you get a positive. Here you have positive flux if the field is flowing out of the surface. And right here you have the field going parallel to the surface, but perpendicular to that vector which represents that little patch of area, and so there is no flux. There is neither field entering nor leaving. And when we talk about the flux of this whole surface, what we want to do is to add up all of the fluxes for each of these little patches, and that gets you the electrical flux for this whole surface. And so we will let those little patches shrink and become infinitesimal, and instead of a discrete summation, we'll do a continuous summation of the flux through each of those little elements. Bing, bing. And this then is the flux for the whole surface. It ought to have an E as well. This continuous summation of these little bits of flux, the field strength dotted with the little infinitesimal of area. Now we have this little circle that has been drawn in the middle of the integral symbol, and that makes it what we call a Gaussian integral. And that circle is indicating the limits of integration. It says, evaluate this integral from some confusing place to some other confusing place so that you go over the whole surface. And what that little dogwood belly button there is it means make sure you go over the whole surface in evaluating your integral. What about the units of flux? Boom, 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 boom. Oh yes. That field would be newtons per coulomb, and area would be square meters, so flux is in Newton meters squared per coulomb. Okay, a checkpoint, and you go ahead and choose one of these. Kind of awkward, but this is a way of breaking it down from 4 questions to just 1 question. Which one of these accurately describes this situation? All right, now Gauss's law. We're finally ready to get to Gauss's law. And what Gauss's law says is that the charge enclosed by a Gaussian surface is equal to epsilon, that's the permittivity constant for free space, times the flux through the surface. And that's it. That's this wonderful thing that I've been touting. We could rewrite it this way, and we'll replace that flux with this Gaussian integral of E dot dA. And this describes this relationship between the field at the Gaussian surface and the charge enclosed. It may not look like much yet, but it is so powerful. Consider this. Here is a Gaussian surface, this bird cage, except we would want to consider it solid, but I'm going to have, instead of electric field, I'm going to have water flowing again. So I needed to have it be a cage so the water could go through it. And we talk about the flux through this Gaussian surface. Well, without this hose, there would be as much water flowing into the surface as out of the surface. And so if you added up the flux over the whole surface, you would get negative flux on this side and positive flux on this side, and it would add up to 0 flux. That's because there is no source of water flow inside. In the case of electricity, this Q is a source of electric field. Now, if you were to put a hose in and you were to squirt water into the cage, I think you can imagine that there would be more water coming out through the cage, more positive flux coming out of the cage than there would be going into the cage. And because there is a net positive flux, I would know that there is a source inside. I would know what the charge inside was by looking at the net flux. Here is another bird cage. This time I have a dentist suction, which looks just like a hose, but it's a dentist suction. It's pulling water out of your mouth so that the dentist can keep working in there while you keep salivating. Well, then I think you can imagine that there would be more water going into the cage than there would be coming out. There would be a net negative flux, and that's because there is a sink inside of the Gaussian surface. Well, we're going to just, here, I'm going to do this in red. If there was a positive charge inside, and it doesn't have to be symmetrical, any place in here, then there would be electric field coming from it, and that, in addition to what other ambient electric field, would mean that there would be net positive flux, net outward electric field dot dA for this thing. And so by knowing that there was net positive flux, I would know there was a positive charge inside. And if there was a negative charge inside, again, it does not have to be symmetrical, This would create a field which went towards the negative charge. That plus this ambient field would mean that there would be a net negative flux, and by looking at that net negative flux I would know what kind of charge was inside of this. And vice versa, by knowing the charge that's in there I would know what the field was like out here. Alright, so here's yet one more example. Here are some charges. Here is the field that they create, and we have drawn a couple of Gaussian surfaces. This is surface 1, and I think it doesn't have very great symmetry about it, but it would be true that there would be net positive flux through that surface, and so I would know that there was a positive charge inside. This surface here, surface 3, would have as much flux going in, that is negative flux, as it would have positive flux. And so we would know from that analysis of the flux that there was no charge inside. Here it's got a net negative flux. I know there's a negative charge inside. This surface 4 here, it may not be obvious by looking at these arrows, but there would be as much flux going out of this surface as there is coming in. And if that is the case, then I know that these two have the same magnitude, that there is no net charge inside if there is zero flux through the surface. Okay, another checkpoint, which is just looking at each of these surfaces and the flux. Remember the conventions for positive and negative, and we have taken 3 questions and boiled them down to just 1. So you can do that. I know you can. Here's a problem. This is a sample problem. Ooh, problems should be so difficult. Here they have a Gaussian surface, and they tell you what the charges on all of these 5 things are, and they put a neutral coin. I think that's just because money gets our attention, and so now we want to do the problem. But note that at this surface, this ugly unsymmetrical surface, there would be field, and the field would come from all 5 of these. The field would arise from charges that are inside and charges that are outside. But the charges that are outside, if you go over the whole surface and look at the flux from the charges that are outside, there will be as much flux in as flux out from those. So if you want to know the flux, what is the net electric flux through the surface, I would ignore these 2. They're going to be flux neutral. It's only the enclosed, and I would find the net charge enclosed and divide it by epsilon naught, and that would be the flux at the surface. Okay, so we're about to start applying Gauss's law, and when you do it, this is another case where Mr. Houghton is going to say you need to do it my way, and you people will say your way doesn't make sense, and so you will decide not to do it my way, and then I will be obligated to take points away from you. I want you to do it my way. I think it is a good way, and if it doesn't make sense to you what I'm asking, then ask me where is the sense in it, and I will explain it to you. And if you are not too hard-headed, you will hear me. So here is the process of going about applying Gauss's law. First, you need to think about the symmetry of the field that you are working with, and to choose a surface that complements that symmetry. So here is a sample. I have a ring of charge, and it's a spherical shell of charge, and I would like to know the field at that place, at that red dot. Here's the task. Find the field at capital R, which is greater than R, which is the radius of this shell. And it's a shell of radius R and charge Q, and it's uniformly charged. So I do get a uniform field that I would think about this thing and I would say, oh, well, the field is going to be going radially out from this thing, and you have to perceive that, or you're just flailing. And so I choose a, here it is, explicitly describe your Gaussian surface. And this may take a little effort to describe it, and I expect you to expend that effort. So here is a typical distribution. My Gaussian surface is a spherical shell of radius capital R, concentric with the charged shell. So much to write, and that is what I expect of you. Then I would expect you next to state Gauss's law. Boom. Then I would expect you to go over, what we've got is a dot product here and an integral. We need to try to choose Gaussian surfaces, and by the symmetrical Gaussian surfaces we can get E, so either it doesn't change as a function of where you are on the surface, which patch dA you're at, or it is perpendicular to that patch dA, so the dot product gets you a 0. That's the kind of surfaces we're going for. So that this is an integral we can evaluate. In this particular case, I would say that E is everywhere parallel to the area, or to the dA if you like, and further that E is everywhere of the same value. Two statements. I want you to make those two statements. How are you going to deal with this dot? What is the angle of E relative to dA? And you're really hoping that it's either parallel or perpendicular. It's the kind of surface you want to choose. And then that E is constant. It is not a function of where you are. And so, because of that, E can be pulled. I'll finish this particular problem, that you have the charge enclosed, which is Q, epsilon naught, and then you have the E is constant, so I can pull it outside the integral, and because it was everywhere parallel, that dot product goes away and you just have a 1 coming out there. And so the E comes outside the integral, and then I'm evaluating this integral going over the whole surface dA. But if you go over the whole surface dA, you get the surface area of a sphere, 4 pi r squared. And then you need to realize that your purpose was to find the field. And so what you want to do is get E by itself. And so you would take the Q, you would divide it by epsilon, and you would divide it by 4 pi r squared, and it should look very familiar. I'll go ahead and do that. Q divided by 4 pi. Oh, you forgot the epsilon, Mr. Houghton. Yes, I meant to write it right here. Epsilon naught r squared. Oh my, you'll say, that looks just like Coulomb's law. That is, the field that you have here is the same as the field you would have if all of that charge that was on this spherical shell was located at the center. It's almost boring if it were not wonderful. How beautifully Coulomb's law comes out of this. Another application, and this is going to be rather tedious, I'm afraid, but I hope that it also makes you feel secure. The task, find the field at distance r from a point charge, not a spherical shell, but a point charge q. Now let's see if we can recall all the steps that Mr. Houghton suggested. First, consider the field from a point charge, and you just consider it. It sits inside your head. But oh, I know what the field looks like from a point charge. It's these radial lines going out. And then you choose a Gaussian surface, and you state explicitly what that Gaussian surface is. It's a sphere of radius r. Because why r? Because that's where I wanted to find the field. So that point that I'm interested in needs to be on the surface, concentric with the charge. And then state Gauss's law, which I hope you will memorize very quickly. And then consider E everywhere on your surface. Let me draw the surface, just so I have this mental image that I'm putting a sphere that is going to be r big because I want to know the field at r. And then I consider that, and I see that the E is everywhere parallel to dA, and E is everywhere constant. That this statement here can get to be like your statements of the net external force is 0, or the change in acceleration is 0, that Mr. Houghton was making you write, and you would just write them whether they were true or not. Don't get into the habit of putting this down just because that's what we always write. Put it down because it is true. And there will be cases where it is not true, and you will have to say E is everywhere parallel on the sides of the cylinder, but E is everywhere perpendicular on the ends of the cylinder, and you will need to write all of that. Make your statement be true. And then, because of that, I can go ahead, and for the charge enclosed, I'll put the Q that is enclosed inside of that surface. E is everywhere parallel to dA, so the dot product just becomes EdA. And then E is everywhere constant, so I pull it outside the integral. Then I'm left with the Gaussian integral of dA, so I go over the whole sphere, and I get this. Of course, if it was a cylinder, you would be getting different values. Okay? And then I recall that what I'm interested in is finding the field, so I isolate the field, and of course, there again, we have Coulomb's law. And this would be said to be a showing of the equivalence of Gauss's law and Coulomb's law. That they are said to be equivalent. However, to do Gauss's law, you need to have this symmetry, or you can't evaluate the integral. If you don't have that symmetry, then you're just going to have to bash it out with Coulomb's law. And that will happen. We're going to run into problems like that where you can't apply Gauss's law. Also, it's perhaps interesting to note that Coulomb's law fails if the charge gets moving too rapidly, that is, relativistically. Gauss's law does, however, continue to work in the relativistic realm. Thank you very much.